Welcome back to Fun with Integration, and Happy New Year as well. This is the first video of 2025, and I'm really excited to start off with Fun with Integration, or Fun with Integrals. I should really get used to saying this name. Like, we're only in episode 3 now, and we have this monstrosity right here. Okay. Now, as much as I can talk about the last video did very well. I think it was the first video to actually break 1,000 views, which I'm actually really proud of. So I feel like I did a good job with that video. I saw some of your comments. I did see the mistakes that you guys pointed out. So thank you so much for pointing out the mistakes that I made. I appreciate it, and it's definitely going to help me out further when I'm making more videos on this channel. Okay, so let's get started with this question. Well, it looks very intimidating, eh? It is intimidating, and it is pretty annoying, right? And it's a definite integral. It's actually a multivariable calculus question, but we can actually kind of manipulate this one, right? And I'm going to show you what we're going to be doing. So we can see that this whole integrand is with respect to x, right? It's the definite integral from x equals to 2 to x equals to 3. That's what we have. But what do we notice within this integral over here, right, with respect to x? We have an integral over here with respect to y, and we have an integral here with respect to z. Now, the first thing you really want to do, right, is just to try and see what are we going to do. Now, clearly we have two different integrals with respect to different variables, and it's a little bit weird, right? So I want to kind of change it up a little bit. But before we can change it up, let's try and solve one of these integrals, because it kind of looks weird. We kind of have a multivariable function that looks something like f of x and y, right? Because we see y is in the numerator, and it's the simplest one that we have in the numerator. Well, not the simplest one, but it makes sense, right? It's kind of linear to the integral that we are dealing with. But let's just deal with this integral. Why am I saying that? Let's just focus on the easy one first. Normally you would like to see where this goes. It is a definite integral, so let's just focus on that one first. So what I'm going to do is I am going to color code, okay? So this one will be red, this integral will be blue, and then this whole integral will be black, okay? So when we get to the final step, because normally finally we work with the integral on the end, the outer side of the entire multivariable integral. Okay, so let's get started with the red one. So what do we have with the red one? We have the integral as from z equals to 0 until z equals to 1 of z multiplied by e to the z with respect to z. Okay, it's a lot of z's, okay. So let's just try and go up a little bit over here. Okay, so the first thing you'd probably want to do is integration by parts, because we have a product, right? We have a z, and then we have e to the z and something with respect to z. And the easiest one that we can differentiate is obviously both of them. But the question is, what is the easiest one to integrate, though? That is the question, right? So the easiest one to integrate is obviously going to be e to the z, because it gives you e to the z, right? So I'll show you what I mean. If we're going to do integration by parts, what we are going to do, we're going to choose our variables quickly, right? So we're going to have the integral, let's choose u and v, our standard ones. So we're going to say the integral of, we're going to keep it at, okay, we have an indefinite, so it's going to be a to b, and then it's going to be of u with respect to v, right? That's what we're going to be dealing with in our case. That's the substitutions. We're going to substitute for u and substitute for dv. And then this will tell us that we are going to get u multiplied by v evaluated from a to b minus the integral from a to b of, it is going to be v with respect to u. We're flipping it around now. Okay. So that's what we want to get. That's what we are going to get if we try and find our variables here. So what we are going to do, we're going to suppose that u will be equal to z. Like we said, it would be easier. Therefore, du will be equal to 1 dz, which is just going to be dz. We don't have to focus on the 1. So now that we've done that, we need to focus on dv. So dv, we can let that be equal to e to the power of z, not v, with respect to z. Now remember that we had z on its own, right? We took it to suppose it's equal to u. Well, now what we are doing over here is we are going to suppose that e to the z with respect to z is equal to dv. Okay, so that we can actually take the integral on both sides. And if you take the integral of dv, it just goes back to its original, which is v. And then this is going to be equal to, what's the integral of e to the z? Well, with respect to z, it's just e to the z. And it is plus c, but at the moment, it's our substitution method. So we're not really going to add the plus c until the end. But guess what? We're not going to put a plus c anyway, because it is a definite integral. We're working with upper and lower limits. So we don't need to focus on this right now. Okay, so now that we have our substitutions, right, we know what v is equal to, and we know what u is equal to, and we know what du is equal to, we can substitute into this right-hand side. Okay, so I'm just gonna quickly move this out of the way so that we can have some space. So this is just gonna be equal to u times v. U is equal to z, and v is equal to e to the z. And this is evaluated from z equals to 0, and z is equal to 1. And this is minus the integral from z equals to 0 to z equals to 1. Okay, and then what we're going to have over here is v is equal to e to the z, and then we're going to have it with respect to, with respect to du, what is du equal to? Du is equal to dz. So we're going to have it with respect to z. That's perfect. That's exactly what we want. Now from here, it's going to be pretty easy to integrate. We can integrate this one now. Okay, so we're going to keep the evaluation part here. Z times e to the z evaluated from z equals 0 to z equals to 1 minus, and then we're going to evaluate here. So we're going to have e to the z evaluated at z equals to 0 and then z equals to 1. And because both of them are evaluated from the same limits, what we can do is we can just combine them together. But do we want to do that? You don't have to do it. But I wouldn't do it though, because then you're putting more terms in. I want to do them separately, so it's easier, right? So let's evaluate z times e to the z first, right? So first of all, what we are going to be using is our f of b minus our f of a. Okay, to evaluate. And what is our a value? Well, or our b value? Our b value is just going to be this one here, and our a value is going to be the lower limit. Okay. So now let's do that. So first of all, we're going to be working with the 1. So it's going to be 1 multiplied by e to the 1. And then this is going to be minus. We're going to have the 0 now. So it's going to be 0 multiplied by e to the 0. Sorry about that. Very untidy. Okay, now that we did that, we're going to minus, remember, because we have a subtraction sign here. I'm going to put a bracket around just because when we have a subtraction, you would normally want to put a bracket afterwards. Now we're going to evaluate e to the z from 0 to 1. So it's first going to start with 1 first. So we're going to plug in the 1. And then over here, we're going to minus it by e to the 0, which is the lower limit. Okay. Now we're just going to simplify over here. What we know over here, this 1 times e to the 1, this is just going to be e to the 1, but we don't really need to write the power of 1. And we know that 0 times anything, in this case over here, any definitive number, we will have 0. So we know that this is just going to be equal to 0. And then the same over here. In this one, we're just going to have 1. And then this one, oh no, but this is actually e to the 0. It's raised to the power of 0. So that means it's not going to be equal to 0. Anything raised to the power of 0 is just equal to 1. Anything but 0 is equal to 1. Okay. So then what we're going to be left with, we're going to have minus, we're going to have e minus 1, like that. And then we can rewrite it like e minus e plus 1. And then this is just going to give us, these are going to cancel. And then here, we're going to be left with 1. So what we are saying over here is that the integral from z equals to 0 to 1 of z times e to the z with respect to z, that is just equal to 1. Meaning, in this integral here, the denominator is just going to be equal to 1. Meaning, we're just going to be left with a linear integral. So I'm going to just cut to the part where I just do the substitution again. Okay, so this is basically what we have, right? I did explain what was going to happen. We have something divided by 1, and anything divided by 1, it just becomes itself, basically. Right? That anything becomes just anything without the divided by 1. You know what I'm saying, right? So what I'm going to do is I'm just going to rewrite it in that way I just explained it. It's going to look like this. Now, would you look at that? Doesn't that look much better? Now we're dealing with a double integral. And it has its multivariable function or integrand in terms of x and y. So that's basically what we have right now. It's a multivariable integral. Sorry, my tongue is twisted here. But anyway, that's what we are left with. And now we are going to, obviously, like I did do in one of my other videos, if you want to check it out, it's double and triple integrals. There should be a card that pops up on the top. You can check that out, how to do double and triple integrals. But now we're doing a double integral, so it's a little bit easier. Would it be easier? No, it's a little bit less work, actually. So this is what we're going to do. So we're going to work with the middle one, which we're going to be doing in blue, actually, because I just did red. So let's do a different color of blue. Like this, right? So that's what we're going to be doing. Okay, so we're going to be working with that one over here. So let me just cut to the part where I actually write it down. Alright, there we go. Now we have our integral separated, right? Now we have it with respect to y. So what we're going to be doing now is we are going to just do the integral simply, right? So we have the integral from y equals to 2 to x squared plus 2. Note how we have a variable x squared plus 2. Or x squared is our variable we're working with in the upper limit. Looks intimidating, but it's actually not that intimidating. You're just going to plug it in at the end because it's a definitive integral. A definite integral. Damn it. So how are we going to integrate this, right? So what I want you to look at, right, is the denominator. And the denominator, we can actually factorize that. And we can factorize it like this. It's going to be y squared minus 2y plus 1. How can we factorize it? Well, clearly, if you have done this in high school, I've been taught this method, so unfortunately you're going to have to deal with this. Otherwise, you can use your factorizing method. What you can see over here, we have two y's being factors of y and y. So we're going to put the y on the left-hand side of both of them because they're on the left-hand side. Then on the right-hand side, we're working with a constant of 1, which can only be factored as 1 times 1. So we have 1 and 1 over here on the right-hand side. And then we look at the sign of negative. The negative pops up first, or with the biggest one, but in this case, any one, because it's both the same number. And then the positive, it's affected by the negative, so a negative and a positive gives a negative, which gives us our next sign. And we can see that this is repeating itself. So we can write this as y minus 1 all squared. And that's what we're going to be having in our denominator. So we're going to have y plus 1 divided by y minus 1 all squared dy. Now this looks a bit weird. You would probably think, oh, let's substitute. But then you realize there's a plus over here. It's ruining the whole question now. It literally ruined my smart moment. I felt so smart for that moment, but now I feel stupid. That's how I felt, by the way, when I was doing this for the first time. I actually made this question up. I just wanted to do it, because why not? Just for the series. So what I want to do is I want to also get y minus 1 somewhere in the numerator. Now, how do I do that? Now, let me just write it over here. So y plus 1. We need to rewrite this in terms of y minus 1. So we can also write it as y plus 1 plus 0. Now, we are going to add 0 to this, meaning that we can add anything we want as long as it cancels itself. Meaning that we can say that 0 is equal to 2, positive 2 minus 2. Or we can say 0 is equal to positive 69 minus 69. They'll cancel out anyway. So what I'm going to do is, because we want a minus 1, we're just going to write it as y plus 1 minus 1. Can you see what I did there? Okay, and then we need to regroup it. So we're going to regroup it as y. We're going to take the negative 1 to that side, right? We can still do that. So it'll be y minus 1, and then we still have 2 plus 1s. So it's plus 1, which we can actually write as y minus 1 plus 2. Can you see how I grouped the y minus 1? which we kind of have here in the denominator. So that's perfect. It's exactly what we need. So that's what I'm going to do right now. We can write y plus 1 as y minus 1 plus 2. So let me rewrite it there. So we're going to have y minus 1 plus 2 divided by, and then we're going to have y minus 1 all squared with respect to y. Okay, great stuff. And now from here, we can do a substitution. It kind of helps us to do a substitution right now. So I'm going to suppose that u is going to be equal to y minus 1, because that's what we want to do, such that du will be equal to, well, the derivative of y with respect to y is just equal to 1, and then derivative of a constant is just 0. So we just left with 1 dy, but we don't need to write the 1 down. So meaning we're going to replace dy with du immediately. Okay, and then we're going to substitute y minus 1 with u. So that's what we're going to do here with this integral. So we're going to have the integral from y equals to 2 until x squared plus 2. And then we're going to have u plus 2 divided by, and because we have y minus 1 all squared, we're going to write u all squared. And this is du. Okay, that's beautiful. That's beautiful stuff. Now what we can do over here, well, we have we have this over here, right? We can actually break this up as u over u squared plus 2 over u squared, because we're actually going to distribute the denominator with the two terms on the numerator. So then this can be simplified. Note I'm just going to simplify it like this so I don't have to waste too many lines. It's going to also be written as, well, we can cancel this. This will be 1 over u. And then this will just be 2 over u squared. Okay, it's plus, by the way. So that's what we have. We have 1 over u plus 2 over u squared with respect to u. And this is from y equals 2 to x squared plus 2. Okay. Well, yeah, we didn't... Also, just note how I didn't change the limit, because it's going to be a waste of time to change the limit, and then it's going to be weird, trust me. I'm going to show you what we can do, though, to not change the limit. So, basically over here, we can distribute the integral to both of these terms. So we can write it as integral from 2 until x squared plus 2 of 1 over u with respect to u plus... And note how we have a constant over here. So we could just take that constant outside of the integral. Then we will have the integral from 2 to x squared plus 2, sorry, my throat, of 1 over u squared du. Okay, so that's basically what we are left with here. But we can rewrite 1 over u squared as u to the negative 1. So that's what I'm going to do over here. I'm going to replace it here to save the lines. 1 over u squared can also be written as u to the negative 2. So now we can straight up just integrate everything, right? So how we integrate this, we're going to say the integral of 1 over u with respect to u is going to be the natural log of the absolute value of u. And then we're going to have it evaluated from y equals to 2 until y equals to x squared plus 2. Okay, this is plus 2 into, what is the integral of u to the negative 2? Well, I'm actually going to do it right here. Integral of u to the negative 2 with respect to u. Well, we can actually write this as, it's going to be u to the negative, well, it's going to be negative 2 plus 1, which is negative 1, divided by, the denominator is the same as the exponent. So it's going to be negative 1. Okay. So what we're going to do over here, well, this can also be written as negative u to the negative 1, which can also be written as negative 1 over u. So we're going to just replace that. So we're going to have multiplied by negative 1 over u, but if we multiply this into the 2, we can see that the negative goes with the positive. So it's actually just going to be minus 2 into 1 over u. And this is going to be evaluated, remember it's still evaluated, from y equals to 2 and y equals to x squared plus 2. Now, because we have a y being evaluated in, we have a u, and that's the problem. But we remember that u is equal to y minus 1. So we can just replace u with y minus 1. So it's going to be the natural log of absolute value y minus 1 evaluated from y equals to 2 to y equals to x squared plus 2 minus 2 into 1 over y minus 1, evaluated, that's not nice, evaluated at from y equals 2 to y equals x squared plus 2. Okay, so now we can just plug the limit into the y. So we're going to be having the natural log of absolute value. We're going to first deal with the upper limit, so it's x squared plus 2, and then it's going to be minus 1. And then we're going to have minus, and it's going to be where we substitute 2 into it. So it's going to be the natural log of absolute value, 2 minus 1. Okay, so that's what we have for the first one, right? Let's do the second one. So the second one, it's minusing 2 into whatever we're going to evaluate into, right? We always take the constant out and the negative, so that we make it easier for ourselves. It's going to be 1 divided by, first we're going to have y is equal to x squared plus 2, so it's going to be x squared plus 2, and what do we have here? It's minus 1. That's left over. This is going to be minus, and then it's going to be 1 over, now it's going to be the lower limit, so it's going to be 2 minus 1. Okay, and then there we go. Now we can simplify it a little bit further because that's what we should do. And what we have over here, well, if we simplify this, we have the natural log. Okay, so let me just get rid of the brackets. So it's the natural logarithm of absolute value x squared, and we have two constants. 2 minus 1 is just equal to positive 1, absolute value, minus the natural log of 2 minus 1. The natural log of 2 minus 1 is just equal to the natural log of absolute value of 1. And what do we know natural log of 1 is? Well, natural log of 1 is just equal to 0, meaning that this will become 0, and we don't need to include it. Okay, then we have 2 into over here, because we're not going to include it, so we don't have to include it. So we're going to do all this part over here. So we have negative 2 into, and then we're going to have 1 over, we're just going to simplify this. We have x squared, and it's going to be 2 minus 1, which is equal to positive 1. And then over here we have minus, and it's going to be 1 over 2 minus 1. 2 minus 1 is just equal to 1, so it's negative 1 over 1, which is just negative 1. Okay. Beautiful stuff. And then we can simplify further. Well, to make the integration easier as well, because we know we're going to integrate all of this again, what do we notice about x squared plus 1? Now, if we were to graph this function on a Cartesian plane, right, where we have the y-axis and the x-axis, we know that x squared plus 1, well, this is the y-intercept, and then we're going to have the function going upwards, concave up. What do you notice here? We need to have some knowledge about natural logarithms. Natural log can only be true if x is going to be greater than 0, right? It's only defined if x is greater than 0. So meaning if we have the natural logarithm of 0, it's undefined. If we have, it's because according to our natural log graph, we know that all the values are going to be greater than 0 because 0 is an asymptote. Okay. You can also, if you want to be a little bit more interactive with this one, I recommend looking up the graph of a natural log if you don't know what it looks like. Okay, I'm not going to show it right now because it's going to waste a little bit more time. I want to keep on to the question right now. But what do we notice about this? It's always positive. This graph of x squared plus 1. It's always positive, meaning we don't need to write this absolute value, because when we have the absolute value of something positive, so if we have absolute value of, let's say, for example, positive 2, right? This is just going to be equal to 2. If we have the absolute value of negative 2, this is equal to positive 2. But remember, whenever we have x, that's going to be the biggest problem. But if we look at our function and we plug in certain values, we always get a positive in x squared plus 1, meaning we don't have to include the absolute value anymore. Okay, so it's going to be x squared plus 1, normal brackets. Then we're going to have minus 2 into, well, I mean, we can just take the minus 2 in now. So it's going to be minus 2 over x squared plus 1. And then what do we have over here? Well, the negative and a negative gives a positive, and this is going to be 2. So this is our final answer for the integral with respect to y. Okay, so it was from this one here. This one. So we dealt with that. Now I'm just going to quickly plug it into the full integral just to see what it looks like. Alright, so it looks like this now, right? We plugged in that integral that we had with respect to y with what we evaluated. Obviously, it's not really a value, but it is in terms of x. And guess what? This is an integral with respect to x. Isn't that perfect? And there is no other variable than x. So now we can just do a very, it's not really a simple integral. It's a simple integral, actually. It's really, really simple. It's just there's a lot to do. We have to do a lot of substitutions here. So get ready, because now this is the final one now. Okay. So what we are going to do is we are going to linearize it, right? So what I'm going to say over here, we're going to take the integral into all of these terms here. Okay. So we're going to have this is going to be equal to the integral x equals to 2 until 3 natural logarithm of x squared plus 1. Can you see how much easier it is now? We don't have to work with the absolute value, otherwise it's going to be a little bit of a problem. And that's what's fortunate about this question, is that we don't have to deal with those problems. This is with respect to x. This is minus the integral of x equals to 2 until 3. This is, well, I mean, now that we have a constant over here, we can take that constant out, actually. So we have 2 over there. This will be 1 over x squared plus 1. Okay, with respect to x. And this will be plus the integral of 2, well, this is going to be from x equals to 2 until 3, 2 dx. And that is what we have here. We basically linearize this integral so that we can distribute the integral with all the terms in the integrand. Okay, so now we have 3 different integrands over here, right? So what we're going to do is, let's just focus on this one. Okay, let's focus on the first one, right? I know this one is the most easiest one, this one over here. This one is the easiest one. Obviously, we can all do this one in our sleep. But this one, let's just focus on this one, right? Because I don't think I've actually made a video on this one. It's an integration by parts one, where you have the natural logarithm of x, right? And then you do all of that stuff. Now, what I want to go to right now is I want to show you what we're going to do. So because I did spend a long time, I did do the solution of this before, but I kind of forgot it because I did it yesterday. So I'm going to do what I feel like I did yesterday, but it should be correct though. Okay, so what I'm going to do, I'm going to color code it again. I know we used red before, but this is red, okay? We're going to say this is red. So this is going to be our integral of x equals, from x equals to 2 until x equals to 3 of the natural log of x squared plus 1 dx. Okay. So let's move down to that one. So now what we can do over here, we are going to use integration by parts. Now we are going to do it in terms of different variables because we already have u and v. So let's just do different integrals, right? So we're going to have the integral. We don't really need to focus. Okay, yeah, let's focus on it. It's going to be a to b of, let's say, t and w. T with respect to w. We're going to work with t and w for this one. Okay. Doesn't matter what variables you use as long as you get to the final answer with respect to x. Okay. As long as you do your substitutions correctly. I'm just used to doing a lot of substitutions, so I should be fine with it. T multiplied by w, evaluated from a to b. And then we're going to have minus the integral of w with respect to t. Okay. And this is from a to b. So now what we're going to do, we're going to try and find, suppose something to be equal to t and something to be equal to dw. Okay, so we're going to suppose that t is going to be equal to, well, taking the derivative of this natural log is pretty easy, easier than taking the integral. That's why we're doing this, by the way. If we were to suppose that the natural log of this was equal to dw, then, I mean, we're just answering this question already. And that's what we are trying to eliminate, right? So we can take the derivative of this easily compared to the integral of that. So we can say that this is going to be equal to the natural log of x squared plus 1. Okay, and then we find the derivative of that. dt equals 2, and then we know that the natural log, we're going to say it's 1 divided by the inside of the bracket x squared plus 1 multiplied by the derivative of the inside of the bracket, which is just going to be 2x. And then the plus 1 is just equal to 0, so we don't have to include it. And this is with respect to x. Okay. Now what we're going to do over here is, I was going to say take the constant over, but don't do that actually. I want to just simplify it a little bit further, make it look a little bit better. It's 2x over x squared plus 1 dx. Okay. Because remember, we found out what dt is equal to. We can substitute it into this over here. So now that we found out dt and t, we need to find out what dw is equal to. We need to find out what w is equal to, but before we can do that, we need to use dw. Okay, dw is equal to something with respect to x, because remember, we didn't use this yet. Now, what else do we have in this integrand that we can actually multiply with respect to x? Well, if you said multiplied by 1, you are absolutely correct. Because, well, we can multiply anything by 1 and we still get the same thing. Isn't that so? So that means we can just say that it's 1 dx. And remember, now we need to take the integral on both sides in order to get w. And this is going to be equal to the integral of 1 with respect to x. This is just going to be x plus c, but we don't need to deal with the plus c because it's a definite integral. And plus, it's just a substitution method. So we got w. It's just x. That's what w is equal to. Now we can do the substitution, but let me just move this out of the way quickly so that we have more space. So this is going to be equal to, it is t times w. T is equal to the natural logarithm of x squared plus 1. And then we're going to have multiplied by w, which is x. Okay, so it's going to be multiplied by x. Minus also we're evaluating it. I almost forgot about that. That's from x equals to 2 until x equals to 3. And this is minus the integral from x equals to 2 until x equals to 3 of, let me just move this a little bit more so we have a little bit more space here. So then we can have w, which is x, and then dt, remember we have dt over here is equal to all of this. It's 2x, so it's multiplied by 2x over x squared plus 1 dx. And that's perfect. That's exactly what we want to do over here. Okay, so let's get a little bit further into this, right? We want to do this integral here. Okay, so this is what we need to do. Well, we still have this one over here, so we're going to leave it like this. We're going to have the natural log. I'm actually going to take the x over to the front because it looks better. So it's x times the natural log of x squared plus 1, evaluated from x equals to 2 until x equals to 3, minus the integral from x equals to 2 until 3. What I want to do, right, I can see that this 2 we can take out as a constant. So we can say minus 2 integral of whatever. Okay. So we have the integral, and then we can multiply this x with the 1 with the numerator, and it'll be x squared over x squared minus 1, plus 1 with respect to x. Now this one would be weird to integrate, right? And I don't recommend doing integration by parts. Please don't do that. I'll show you what we can do. Let me do it in a different color here. Okay. So we have over here this integral. Okay. Now let's focus on the integrand of this integral. Okay. So what I want to focus on over here is x squared. So we have x squared over x squared plus 1. Okay. And what we can do is we want to manipulate it so that we have an easier integral for us to solve, right? So this can also be written as, we can also add a plus 0, by the way, so that we can say x squared plus 1 minus 1, such that we get x squared plus 1 over here, and we have x squared plus 1 over here as well. Isn't that amazing, actually? It works out perfectly. Then we can rewrite this as x squared plus 1 over x squared plus 1. This will be minus because of the minus over here. It will be minus 1 over x squared plus 1. We distributed the denominator with both the terms. And what do we notice? We can cancel this out. It will be 1 minus 1 over x squared plus 1. So that's a little bit better in our case, because now we got rid of the x squared. So we're just going to replace this with that, what we had in the integrand. So it will be I'm just going to cut to when I actually get the damn integral part. Okay, apologies about that. We have this now. Okay. So easily we can just distribute this integral, right? So I'm going to cut to that part. And oh my goodness, we are here. Doesn't this look kind of familiar now, what we have over here? Yes, it does. Well, this one is easier to integrate now. We can actually write this. We can actually evaluate this with this one over here, right? So I'm going to do that right now. So we have x, natural log x squared plus 1, evaluated from x equals to 2 until x equals to 3, minus 2 into the integral of 1 dx is just equal to x, and this is evaluated at x equals to 1 until x equals to 3. Okay, so that's what we're doing right now. We're just evaluating that now, since we do already have 1 evaluated. So this is going to be plus 2 into the integral of, with x equals to 2 until x equals to 3. This is where we do trig substitution. Note that we can write this as 1 square, and guess what? We have 2 perfect squares. Now what I want to do over here is I want to suppose, and I'm going to zoom out a little bit over here, I'm going to suppose that the variable that we are using, x, is going to be equal to, well, first of all, let me just remind you about the trig substitution before I just directly go into it, right? Assuming that you know it. I'm just going to quickly recap. Whenever we have anything with a variable squared plus a constant squared, we are going to substitute with tangent of a certain variable. We're going to say tangent theta for now. So it doesn't matter actually what the order is because we have a plus, but whenever we have a plus and we have 2 perfect squares in the integral, you would normally use the trig substitution with tangent theta. So we're going to suppose that x, with the variable that we were using here, is going to be equal to the a value, which is 1, so we don't have to write that down. So it's going to be x is equal to tangent of theta. We're going to use tangent theta because that's a good variable to use right now. It's an angle. And then when we derive on both sides, it's going to be dx is equal to secant, that was terrible, secant squared theta with respect to theta. Okay, so that's what we have right now. So let me move this one here. And that looks sloppy right now. So yeah, we have x squared plus a squared, like that. Okay, now we can just do the substitution, right? That's why I wanted to leave this little space out over here. So if we're doing the substitution, we are going to replace x with tangent theta. And over here it's x squared. So tangent theta squared is just equal to tangent square theta. And this is plus 1. 1 squared is just equal to 1, so we don't have to worry about it. And then the dx is equal to, well, we have d theta outside here. We also have secant square theta, which we're going to put in the numerator. Secant square theta. Isn't that beautiful? And what do we know about tangent square theta plus 1? Well, we know the identity that tells us that tangent, well, I mean, you can also write it as 1 plus tangent square theta equals to secant square theta. We know that the I tan to look sexy is the identity taught by my lecturer. Absolute legend of a lecturer, by the way. Yeah, so this is just going to be equal to secant square theta, which is also repeating in the numerator, right? Meaning they're going to cancel out. So I can just cancel them out from here, right? Because I know what's going to go on. I'm not going to waste so much time just writing everything down step by step. I can just show the lecturer on the side note, we know that 1 plus tan square theta equals secant square theta. That means I can cancel them out. So you don't have to be so restricted to always doing one step at a time. You can even skip through if you're so confident. I don't normally recommend it. If you have experience with mathematics, go for it. But if you're still like kind of learning, just take it one step at a time. You'll get used to it, trust me. Don't rush it. Okay. So I'm just going to skip to the part where I actually have the thing simplified. Okay, so what we have over here is 1d theta. And note how I didn't change the upper and lower limits because it's not necessary at all to change them. So from here, we're just going to integrate that. So what we're going to be left with, and I'm going to keep this part in, so it's a natural log of x squared plus 1 evaluated from x equals to 2 until x equals to 3 minus 2x evaluated from x equals to 2 until x equals to 3 plus, and then we know this is going to be 2x. Okay, because it's 2 theta. I almost messed up there. It's 2 theta evaluated from x equals to 2 until x equals to 3. Okay. Now this is where it gets weird. Okay. Well, we have x on both of these over here, evaluated with x. That's perfect. But this one is theta. So what I'm going to do, right, what is theta equal to? Well, we don't know yet. We do know x is equal to tangent theta. But that's not really going to help us now. So what we are going to do over here is we are going to continue it. We are going to swap it around here. We're going to say tangent theta is equal to x. It's the same thing, but it's obviously swapped around. Then we're going to take the tangent over as arctangent of x. Okay, so that's what our theta is equal to. So it's going to be theta, we're going to replace it with arctangent x. Okay. So that's what we're going to do. So what I'm going to do over here is I'm just going to get rid of this. I'm going to move this here. And then we have 2 arctangent x. Okay. Great stuff. Now over here, well, what we are going to be doing is we just want to evaluate this, right? Let's first evaluate this, and then I'll show you what's going to happen. Note how we still at the first part of the main integral. So yeah, crazy stuff, eh? So let's just evaluate here. It's going to be x. What is the first one? It's going to be the upper limit. So it's going to be 3 natural log of 3 square plus 1 minus, it's going to be 2 natural log of 2 square plus 1. Okay, that's in our first bracket. Minus, I'm going to have 2 into, we're going to take the constant and the negative out as usual. We're going to have negative 2 into, and then we're going to evaluate the x's. It's going to be 3 minus 2. Plus the 2 we're going to take out there. Then we're going to be, okay, so let me write it down here actually, because I noticed what it's going to be. It's going to be arctangent of 3 minus arctangent of 2 when we're evaluating from 2 to 3. Okay. Maybe I can fit it. Let me just test my luck over here. Please, please, please. Nope, absolutely not. So that's why I kept it here. Okay, great. And then let's just simplify it a little bit further because, I mean, why not? It's better to simplify it first so we don't have so much to write and remember. So over here, what we're going to do, we're going to get rid of the brackets. It's going to be 3 natural log of 3 square is equal to 9. So this is 9 plus 1. Let me just do it in a different color here. So we know this is going to be 9 plus 1. What is 9 plus 1 equal to? It's equal to 10. So which means this is going to be the natural logarithm of 10. Minus 2 into the natural logarithm of, we can see this is going to be 4. 2 squares is equal to 4 plus 1, that's equal to 5. Right? So we're going to have the natural logarithm of 5 over here. Minus, we know that 3 minus 2 is equal to 1, meaning we're just going to have minus 2. This is going to be plus 2 into, well, we're going to have arctangent over here. Well, we can't really evaluate this now because we can't really evaluate it right now. So this is going to be 2. We're going to take the 2 in rather. Arctangent of 3 minus 2 into arctangent of 2. So this is what we have right now. This is the line we have for, guess which one it is? This one. This one right over here, that's what we have for. Now we need to deal with the other one, which is that one. So, hear me out, okay? This one is not that bad though. The reason is because, doesn't this look familiar? We've dealt with this already. Over here. We dealt with it somewhere over here, except the constant outside is positive 2 here, but this one is negative 2 outside here. So it makes it a little bit easier. We're really just integrating with this. So we can just go straight up. So I'm going to do it in blue, by the way. So I'm actually going to cut to the part where I put the integrals separately so we can actually sort it out from there. I'll show you what we're going to do. Okay, so this is basically what we have, right? And this will be equal to something. Now let's just focus on the from the integral until dx, right? Let's not focus on the negative 2. Let's just write the negative 2 down over here. What do we know the integral of 1 over x squared plus 1 is equal to? Let's just go back to our working over here. Somewhere here, right? So let's focus on this part here. We know that we did the substitution, the trig substitution. We don't need to change anything. It's going to be the exact same thing, right? So meaning we can just directly do the substitution. Okay, so this will obviously be equal to 1d theta, right? So we know that this over here is going to be equal to 1d theta. So that's what we're going to replace, right? So that's how we're going to write it. But instead we have a negative 2 outside. So it's x equals to 2 until 3, and it'll be 1d theta. Okay, so we didn't really need to. You could make a little bit of a note over there saying, using as reference to your lecture when they mark this, maybe if you get some question like this in the examination where you have two trig substitutions which are basically the same thing, then you can basically make a note of that. Okay, so over here, well, we know that we can integrate it like this. It's going to be negative 2 into theta, evaluated from x equals to 2 until x equals to 3. Okay, and then what we note over here is that we know that theta is equal to arctangent of x. Okay, so I'm going to move this here. So this is going to be 2 arctangent of x. Okay, then we're just going to evaluate that quickly. We can evaluate it like this. It's going to be negative 2 into arctangent of the upper limit, which is 3. This is minus the arctangent of the lower limit, which is 2. And then we can distribute the negative 2 into both of them. Negative 2 arctangent of 3 plus 2 arctangent of 2. And that's what we have over here. So that is the one from here, from this integral over here. Now we can just do this one straight up. Well, we know that this is just, let me just do it over here, right? I'm going to focus on here. Let's just keep using black for now. I'm going to do it here. The integral from x equals 2 to 3 of 2 dx is just going to be equal to 2x evaluated from x equals to 2 until x equals to 3. And then basically what we will have, it's going to be 2 into, it's going to be 3 minus 2, because we're doing the evaluation. That's just equal to 2, positive 2. Okay, I'm sure that you should know how I did it right now. I've been doing it the whole video. So basically this integral here is equal to 2, positive 2. So what I'm going to do is I'm going to take all of them. We know that the red integral is equal to this whole line over here. We know that the blue integral is equal to this whole line over here. And then the black integral that I just did right now is equal to positive 2. So I'm going to cut to the part where I just have all of the values laid out on top of each other, or next to each other. Okay, so from this point over here, I basically put all of them together. So note how this one on the top was the red, this one here was the blue, and this one was our black one that we dealt with. So now what we have to do is we just need to simplify. And this works out so well, and it's so amazing. I'm going to show you what's going to happen, right? Where's the constants? Let's first work with the constants. Well, all of them are constants. What am I trying to say? The simple constants where it doesn't have any natural log or tangent. We have negative 2 over here, and we have positive 2 here. Is there any other like that? No. It's minus 2 plus 2. Guess what? They cancel. Let's work with the arctangents, right? We have positive arctangent of 3. And where's the other arctangent of 3? Negative 2 arctangent of 3. Do you realize that these can also cancel out? Over here, we have negative 2 arctangent of 2 and positive 2 arctangent of 2. Those can also cancel out. And what we are left with is just this part over here. So I'm going to write it here. This is going to be equal to 3 natural log of 10 minus 2 to the natural log of 5. Now this is the final answer. But let me just try and approximate it for you. Okay. This approximates to 3, 688879. Okay. So that's the answer for this integral over here. That's the final answer. Crazy stuff, eh?